Hi, good morning, everyone, and welcome to our webinar, How to Simplify Life Cycle Assessment in Deep Geothermal Projects with the novel GEOENVI tool. I'm Valeria Mazzagatti, Head of Communication at EGEC, the European Geothermal Energy Council. EGEC is a non-profit organization that represents the entire geothermal sector at European level in Brussels. We have also the pleasure to coordinate GEOENVI, which is a European-funded project that aims at answering environmental concerns of deep geothermal projects that are operational or in development in Europe. One way to do so is the life cycle assessment, but our speakers will go through this today into more details. For your information, we have 150 people registered to this webinar, and includes geothermal developers, energy players, ministries, public authorities, universities, and academia. Also, consider that the webinar is recorded and will be made available with the presentations after the webinar. Now I dive directly into the agenda. And you see here we will start introducing the GEOENVI project and the harmonized methodologies for environmental impact assessment. Then we will have a presentation of the guidelines to perform environmental assessment for geothermal system. We have a presentation of the methodology to generate simplified models and the presentation of the 3 GEOENVI case studies of France, Italy, and Belgium. At the end, we have 15 minutes for question and answers, but during the presentation, you can already use the question box at the bottom of the GoToWebinar panel, and you can start writing your questions. Also specify, please, the person who is directed to.
Valeria, sorry, we can see your screen.
You can't see the screen?
No. Okay, no, it's good. No. You closed it down again? Yeah.
Can you see it?
Yes, we can see now. Thanks.
Okay, perfect. Here you can see the agenda. Okay. Right, so I was going through the agenda, and the last point is question and answer. So as I was saying, if you want to have a conversation, if you want to have a discussion with the speakers, please just raise your hand and then we will unmute you. Otherwise, you just write your questions and we will read them at the end of the presentation for the speakers to answer. Now I give the floor to Sylvia Raquel Gudjonstjord, that is expert and project manager at Orkustfum, the National Energy Agency of Iceland.
Thank you, Valeria. Can I share my screen?
Not yet.
Yes, you should be able to share your screen now. Okay, we can see it.
Now, yes.
Okay, how does it look? Is it okay?
Yeah, it's great.
Okay, then I'll just start. Good morning, everyone. I'm Sylvia, and today I'm going to give you a short overview of the GEOENVI project and the harmonized methodology for environmental impact assessment with LCA for geothermal systems that we are currently working on. Little on where the project comes from. The advantages of using geothermal for power production and heating and cooling are not widely known. Recently, deep geothermal energy production in some regions is confronted with a negative perception in terms of environmental performance, which could seriously hamper its market uptake. Media reports focus more on disadvantages than advantages. As a result, decision makers and potential investors have concerns about possible environmental impacts and risk involved in implementing geothermal projects, and social resistance often result in practical obstacles such as significant slowdowns to the deployment of the deep geothermal resources. The GEOENVI project answers 3 important market uptake challenges: a recommendation for harmonization of regulations, life cycle assessment approaches, environmental impact methodologies of renewable energy solutions, development of tools, methods, and models for environmental impact assessment of renewable energy projects, development of tool service using global Earth observation data to support development and deployment of renewable energy sources. The GEOENVI participants, you can see them on the screen now. They are from 6 countries, Belgium, Italy, France, Hungary, Iceland, and Turkey. We have 3 key actors in the project, public environmental institutions and regulatory authorities that implement and or make the environmental regulations. They will exchange on best practices, tend to adopt the GEOENVI recommendations and methodologies, and envisage in harmonization of their environmental regulations. Industry and project developers which develop geothermal projects, they will be consulted on environmental impact and LCA and be asked to implement methodologies and tools. Scientific experts to guarantee sustainability, they will support drafting of environmental regulations for the legislatures and design methodologies and tools on environmental impact and LCA for industry. These are the 6 countries I spoke about earlier involved in the GEOENVI project, but the objective is to cover the rest of Europe at later stages. This is an overview of the work packages in the GEOENVI project, but today we are focusing on work package 3 on LCA approaches. We have 4 tasks within work package 3 that are all related to LCA methodology. Within each task, we have several deliverables to be completed within a given time frame. 2 deliverables have already been completed, and one of them is deliverable 3.2, which is focused on LCA guidelines and to be applied to GEOENVI case studies. The explanation of these guidelines. The guidelines are a key milestone of the work package, and with a publication, it will be a fundamental tool to offer methodological indication and assistance on how to perform LCA of geothermal systems with a common and accepted base, allowing for comparison of results for different geothermal settings and energy conversion technologies. The aim of the guidelines is to reduce LCA result variability, aligning methodological inconsistencies in published LCAs, such as different system boundaries, the use of outdated data, variation on similar energy processes change, and even simple differences in reporting of results. Guidance is given on geothermal specific parameters used as inputs in LCA, on choices in life cycle inventory, data collection, and on modeling approaches and methodological assumptions resulting in the life cycle impact assessment and the interpretation of reporting of the study. In short summary, these guidelines are a first proposal based on expert judgment from GEOENVI partners. They are to be shared among the geothermal community to be revised in order to reach a broader consensus. Regarding the second part of the harmonized methodology, we are in the process of generating simplified parameterized models for selection of GEOENVI case studies to simplify comprehensive life cycle assessment models into reduced models that allow estimation of life cycle impact based on a very low number of input parameters. The target group is non-LCA experts. Further information on the LCA guidelines and the simplified models will be provided in the upcoming presentations. Thank you.
Thank you very much, Silvia. Now I would like to give the floor to Maria Laura Parisi, who is Assistant Professor at the University of Siena and Associate Researcher at the Center for Colloid and Surface that works under the supervision of the Italian Ministry for University and Scientific Research. And she will present the guidelines to perform life cycle assessment. Maria Laura, The floor is yours.
Everybody.
We can see your screen, but we can't hear you well.
Okay, so hello everybody. I'm Maria Laura Parisi from the University of Siena, and I will give you in this presentation a brief overview of the extensive work we performed in the GEOENVI for the definition of the guidelines to perform life cycle assessment of geothermal systems. And I will just show you a very brief application of the guidelines to the Italian case studies of the Bagnore power plants. Developed to offer guidance for consistency, balance, and quality, and eventually to enhance the credibility of the findings from life cycle assessments on geothermal systems. This document covered the most sensitive aspects of each step of LCA applied to geothermal systems, and they've been conceived in order to reach out all the LCA practitioners involved in geothermal systems environmental assessment and geothermal experts. The challenge was to produce in a concise manner guidelines ready to use for any type of geothermal installations, fulfilling the life cycle assessment ISO standards, so the ISO 14 and 40 family standards. The objective of these guidelines were to provide guidance on how to establish and compile the life cycle inventory of geothermal systems, on how to select the life cycle impact assessment method and impact category indicators, and more in general, to provide guidance on how and what to document regarding the life cycle assessment of geothermal energy. The wider scope of these guidelines is to allow to get LCA results that could contribute to a sustainability assessment of the geothermal projects, and does not pretend to be exhaustive and exclusive in examining all the potential environmental issues. This means that the LCA could be combined and integrated by other environmental assessment criteria, which can consider different aspects, for example, site-dependent methods like microseismicity, subsidence, noise, or whose evaluation involves social or qualitative acceptance, like preservation of landscape, cultural heritage, effects on occupations and economics, and so on. Just to go a little bit deeper on the format and methodology of the document, these are a synthetic guidelines in 30 pages, which are combined and completed with foreseen technical appendixes based on outcomes and data issued from the GEOENVI case studies for the application, and all the specificities of the combined heat and power installations. Side of the main methodological issue covered by these guidelines. For the functional unit, the definition of the functional unit, there will be three possibilities to define the system, if it is only for power production or heating and cooling production, or if it is a multifunctional approach. Quite detailed section is devoted to the system boundaries definitions, and it consists in the system under investigation to be divided into three modules, which is the upstream, the core, and the downstream modules. And in any case, the core module must be always included in the LCA of a geothermal system. And the core module is represented by the construction of the infrastructure, the operation, maintenance, and end-of-life phases. Also, indications about the lifetime for the geothermal power plant project is given and is set to 30 years. A dedicated section is given for the multifunctionality of the investigated system, whenever it is the case, and the selection of an appropriate allocation procedure. In this case, if the share between the co-products, energy and heat, is higher than 75%, a system expansion with a substitution model for the co-products is invited as the preferred method to be applied. If the share between the co-products is lower than 75%, then an exergy content allocation method is suggested. The application of these methodological issues to the Italian case studies, for which the goal of the study was set to be the assessment of the potential environmental impact associated with the production of only electricity from the Italian geothermal power plants of Bagnoli 3 and 4. The functional unit was set to the kilowatt hour of net electricity produced over the entire life cycle of the two power plants, and system boundaries were defined in order to have all the background processes represented by secondary data, and to have the foreground system composed by the commissioning, the use phase, and the decommissioning, meaning the the closure of the wells of the geothermal power plant. In this case, the was the exergy allocation one, and because it takes into account the quality of the two energy products, section giving insight of the representativeness of data and quality of data is dedicated in the study, and a very clear list of the main assumptions taken for the development of the study has to be cycle inventory on which the life cycle assessment study has to be developed, describes the materials and energy requirements to build the subsurface, the surface infrastructure, equipment components, and drilling of the wells. The guidelines contained recommendations on the reporting of the type of direct emissions and the receiving compartment, so airborne, soil-borne, or waterborne, and related to each of these subsystems. The use of primary data is priority, otherwise reference and average values will be given in the technical appendixes of the guidelines. And at least, because it's a very important part of the life cycle assessment, is the approach used in these guidelines concerning the life cycle impact assessment method. In our case, in the GEOENVI case, a selection of impact indicators is proposed, and these are based on the last update of the life cycle impact assessment method proposed by the European Commission Joint Research Center that actually have developed and has been testing the environmental footprint version 3.0. In this document, some peculiarities of those indicators will be given concerning the level of priority, which will be specific to geothermal installations, and the level of robustness for the indicator, which is scientifically grounded. is devoted to how to report inorganic emissions and toxicity impacts, which we know to be a very critic part of for the geothermal installations environmental assessment, and inspections on additional indicators like primary energy saving and energy payback time is given. In the last part of the document, there is a sort of detailed list on how to report and communicate the results of the life cycle assessment. So concerning the methodological setting, the parameter choices performed to develop the study, the LCI details and the assumptions, and how to report in figure and table captures. Thank you for your attention.
Many thanks, Maria Laura. Now I give the floor to Isabelle Blanc, who is professor at Mines Paris Tech, the Paris Institute of Engineering, Research and Innovation. She will present the methodology to generate simplified models. And we can see your screen. There you go.
Thanks. Thanks, Valeria. So I guess everybody can see my screen?
Yes.
Yes, okay. So how to simplify life cycle assessment for deep geothermal projects? This morning, I'm going to present the method, the protocol to generate such simplified models. It takes time to move to the second slide.
Try to click on the screen, maybe with the mouse.
Sure. So first, two questions. Why simplified models and how to use them? RCA is time and data consuming, as you have just been reported by Laura. We had within GEOENVI project to start the work by defining appropriate relevant guidelines to apply RCA for geothermal systems. And this is time and data consuming to perform an RCA. But stakeholders are not RCA experts. So here we need to have a new type of models, a simplified one, to be able to disseminate the knowledge of environmental performance for geothermal systems with new type of approach. Fortunately, within GEOENVI project, we have case studies that we have been used and to test this simplified approach. And today we are going to report two simplified models we developed applying the new approach I'm going to present. Just remember that for each impact category, you need a simplified model, and that a range of operation parameters and type of geothermal technology per simplified model. Let's start with an example of a simplified model for an EGS installation producing electricity. Here we have a simplified model based on only 3 parameters, able to provide a carbon footprint of a geothermal, an EGS installation. So here, this simplified model is based on the power of the organic ranking cycle, the well depth, and the number of wells. Such simplified model has been presented at the last World Geothermal Congress. So how do you apply this? Well, simply you specify for these three variables your parameters. So here we apply this model for 2 wells, a depth of 3,800 meters, and a power of 1,200 kilowatt for the ORC. And the answer is, applying this equation, for the carbon footprint is 51 grams of CO2 equivalent per kilowatt hour, meaning that the carbon footprint is given over the whole lifetime of the installation. Okay, so we have this equation, this simplified model. It provides in a few minutes an answer, but is it relevant? So on the next slide here, we have the comparison with a published installation, EGS installation, Stephanie Frick publication, and for the same configuration, that means 2 wells, 3,800 depth for the well, and the same power for the ORC, the publication is giving 54 grams of CO2 equivalent per kilowatt hour, the red dot. And so this is quite close to what is given the simplified model. So that feeds the interest of such simplified model, revealing its relevance. So now the question is, how do we generate this simplified model? It is a 5-step protocol. First one, we have to define on the scope of the study. Of course, we have different type of conversion technology, dry steam, flash, binary. We also have different type of energy. It could be heat production, electricity production. The level also of direct emissions is also important. So you have first to decide on the scope of your study. Then the second step is to define a reference LCA model. And this is the big part of the method. You have to define your variables and the input variables, as well as the range the variables should cover. So you have to model your installation to have a reference LCA model. Third steps, it is a statistical process where you identify key variables inducing the most variability for each impact category. Fourth steps, you generate your simplified model based on the key variables you just identified, and then you validate your simplified model with literature. Step one, within GEOENVI project, we have access to several case studies. And so we can have a good selection of different situations, whether heat or electricity production, EGS or flash hydrothermal. So we are going to propose you different simplified models in accordance with the different case studies we have available in GEOENVI project. So the protocol itself, as I said, first step, scope of the study. Step two, you have to generate your reference LCA model. So it is an explicit step where you have to define your variables, and the range over the variables are going to provide results for your LCA models. Then step three, you go through a statistical selection using global sensitivity analysis. And step four, you have produced your simplified model based on key variables. So we call it a parameterized model. Then you compare your simplified model with literature, step 5. And depending on the results on this comparison, you might go through a revision of the scope of your study. If you don't happy with the scope of the study, you can revise it either by extending the boundaries of your variables, or adding new variables, or restricting the boundaries. So this is an iterative process to go through. This has been published originally for wind power systems in environmental science and technology. So that was step 1. Step 2, as I said, we have to go through the definition of a parameterized LCA model. So you have first to explicitly define your life cycle inventory, select your input variables. You can go up to 20, even 30 input variables and defining the appropriate boundaries. Go through a stochastic simulation, generate your impact results, and generate your environmental profile. So this is going to be the set of the reference set for your simplified model. So as an example here for the Rittershofen heat generation plant, here you have a graph showing in blue the input variables we have defined and for the construction part. So it takes time to define your reference LCA model. Step 3. This is a statistical step where you select your key variables. So how? We apply on the reference LCA model a global sensitivity analysis. This step is very important because it allows you to assess simultaneously the variability of all input variables you decided on. So you could have the simultaneous variability for 20 or even 30 input variables. Then once you have done through that, you can use the Sobol indices to help you to understand which are the one explaining most of the variability. And so you have a hierarchy among your variables. And so you are able to choose the first, I would say, 4 to 5 ones explaining most of the variabilities. So key parameters are the one, when varied, are inducing the biggest variability on the environmental performance. Step 4. So here, back to the example of the EGS producing electricity, we were able to come with a simplified model with 3 variables. And this 3 variables model is explaining 75% of the variability for the greenhouse gases issued from the stochastic scenarios on the reference model. And here on the graph, you can see that we compare the simplified model based on 3 variables to the reference model, which had originally 9 variables. So the results is not too bad, with an A2 of 0.7. And this has been published in the WGC, the last one. So thank you very much for this short explanation on the protocol. Now we have decided to show you the application of this protocol for 2 simplified models, the Rittershofen one and the Bagnoret one, and we also have under working the BioMat case study. So thank you.
Thank you very much, Isabel. And indeed, now we will have the presentation of the 3 case studies. And we will start with Rittershofen in France with Guillaume Ravier, who is engineer at GEOThermal, the expert study department of the electricity utility of Strasbourg, which is specialized in deep geothermal energy. And also Mélanie Duziec, who is tenure track as assistant professor at Mines ParisTech and expert at Armin, a non-profit organization, research and technological organization. So Guillaume Ravier will be the first one to present.
Can you see my screen?
Yes.
So good morning, everybody. My name is Guillaume Ravier, and today I will present you the Rittershofen geothermal heat plant. So this geothermal heat plant is located in the east of France in the Ypres Graben. This project started in 2005, and it is involving 3 shareholders: Electricity of Strasbourg, Roquette Frères, and Caisse des Dépôts et de Consignation. The aim of this project was to supply heat to a starch plant located in Bannheim in France, close to the Rhine River. This starch plant is transforming every day 2,000 tons of corn and wheat, and the total heat demand of the starch plant is about 80 megawatts. So the project was supposed to provide about 24 megawatts of heat and about 180 gigawatt per year. So the targeted reservoir of this project is a sandstone and carboniferous granite located at 2,500 meters deep. The bottom hole temperature is about 177 degrees Celsius, and this project is based on 2 wells. So 1 production well, which was drilled in 2014, and 1 injection well, which was drilled in 2012. Due to very low productivity index of the first well drilled in 2012, it was necessary to enhance this well. So an intensive program of stimulation was performed between April and July 2013, including thermal stimulation, chemical stimulation, and hydraulic stimulation. Maximal pressure reached during hydraulic stimulation was about 35 bar, which is quite low, and no induced seismicity could be felt by the local population. So due to this intensive campaign of stimulation, this project is classified as enhanced geothermal system. On the contrary, the second well, GRT2, was very good after drilling, so it was not necessary to enhance this well. The brine of this project is a sodium, calcium, potassium chloride dominated brine with a total dissolved solid of 100 grams per liter. The total and non-condensable gas is about 0.24% in mass. So the heat plant was built between 2015 and 2016 and is in operation since May 2016, so nearly 4 years now. This heat plant is designed with 2 loops, one primary loop with brine and one second transport loop with fresh water to transport the heat from the geothermal power plant to the starch plant. So this geothermal plant is designed with a pressurized geothermal loop with a pressure higher than 25 bar, and this allows to keep all the gas dissolved in the brine, so there is no non-condensable gas emission during operation. This plant is using a downhole production line shaft pump and 12 heat exchangers in series. So the heat capacity of this geothermal plant is about 27.5 megawatt thermal. And the total electrical consumption of this heat plant is about 550 kilowatts, including the consumption of the downhole production pump, but also for the pump to the transport loop. And as you can see below, the Rittershofen plant is located at more or less 12 kilometers from the starch plant, and there is a district heating between both, a 15 kilometers long transport loop installed at 1 meter deep in the ground. So some information about the operational data of last year. The wellhead temperature was 168 degrees Celsius, the average production flow rate about 280 cubic meters per hour, and the plant was stopped 2 weeks for maintenance. So the availability of the plant was in 2009 about 96%. Main failure were external due to electrical grids. And the thermal losses between Rittershofen and the starch plant on the 15 kilometers is lower than 4 degrees Celsius, which is quite low. The geothermal plant produced about 193 gigawatt of heat, and the heat user consume about 175 gigawatt of heat. The difference is the thermal losses in the district heating. So the average power of the heat user was 21 megawatts, and this project saved about 43,000 tons of CO2 from natural gas burning. So now I give the floor to Melanie.
Hello, can you all see my screen?
Yes.
Good morning also from my side. As mentioned by Valeria and Guillaume, I will now continue on presenting the simplified model for Rittershofen. First, we will start with the definition of the reference parameterized LCA model. Then I will go on by identifying the key variables of this model. I will present the simplified model that we derived for climate change and validate or spend a few words on the validation of the simplified model with literature. Here, the reference parameterized LCA model, I will be referring to it also as reference model. And what I mean is what Isabelle Blanc already mentioned, that the Rittershofen case study was used to derive a model that is as general as possible to represent an enhanced geothermal system for heat production. And then I will also be talking about the simplified model, which is developed to estimate the amount of CO2 emissions emitted for specific boundaries of different variables during the life cycle of enhanced geothermal system for heat generation. First of all, to define this reference parameterized life cycle assessment model, it's necessary to think about all the different life cycle stages of the power plant that we want to model, and think about all the variables that might be important to consider. In the exploration phase, it's important to think about the amount of energy that is required during this exploration phase. We assign a distribution to this variable, which has boundaries as mentioned on the slide, and the distribution is uniform so that any value within this range can be used. You can also see that the energy for exploration is highlighted in a bluish tone, which means that it's a parameter that is specific for installations that are located on not volcanic grounds. After the exploration phase, the next stage consists in the construction of the plant. So on the one hand, the construction of the power plant in itself, and on the other hand, the drilling of the well. For the power plant, the important aspect is the heat exchanger, which I modeled using a variable for the length of the fresh water pipe and the length of the geothermal water pipe. With this value, I could then derive the amount of materials that are necessary to build those two pipe types. And then I also used the mass of the heat exchanger in Rittershofen to derive, using a proportionality rule, for any other mass of heat exchanger the amount of materials that are required. You can see that these parameters are highlighted in orange, which means that they are specific for installations that produce heat. Another aspect that is important is to take into account the production and the injection pump. The production pump is a line shaft pump, which has a power output between 200 and 1,200 kilowatts, and the re-injection pump will have a power between 0 and 500. So for some installation, it's not necessary to use power to re-inject the fluid. Those parameters are highlighted in deep blue because they are general for any type of geothermal installation. You're likely to find them again. Another important part is the building in itself, so the building that houses all the electrical equipment, and the materials required for this building, they depend on the area of the power plant. Besides the construction of the power plant in itself, we also have the drilling of the well, which depends on the length of the well, but also on the ratio between the meters drilled and the well length, because the meters that are actually drilled might be longer than the well length. Then I also took into account that some installation might have 1 to 2 wells in terms of injection and production. And finally, it's also important to consider that the cuttings that are produced during the well drilling might need to be transported to the treatment site, which is why I use this parameter. Here I should also mention that I modeled the same well for the injection and the production. So the well length specified here is for one single well. For the well drilling, another important aspect is the drilling platform. And here again, the materials requirements scale with the size or the area of the platform. Then an important part for these enhanced geothermal systems is the stimulation part. I accounted for the chemical stimulation and the hydraulic stimulation using the volume, from which I derived energy requirements and also the material requirements for the chemical stimulation. And finally, once the wells are drilled, it's important to do some testing. And during this testing phase, CO2 is emitted into the air. After the exploration, the construction phase comes the operation and maintenance phase. Here it's important to take into account the amount of direct emissions, which can consist of CO2 or methane. Those are the two gases that we took into account here, because we assume that these installations typically have low direct emissions. We also took into account the flow rate, the lifetime, and the operating hours to estimate how much scaling inhibitor, how much corrosion inhibitor, how much salt, or also how much water is used for blasting during those operation and maintenance phase. And here it's also important to mention that the Rittershofen power plant and in general that these heat generating power plants will require electricity to run the pump during operation and maintenance phase, so that the electricity requirements during operation and maintenance phase needs to be accounted for and is directly dependent on the power of the pump. And because we want to have the impact in terms of kilowatt hour heat produced, we also took into account the heat output of the plant. And I also considered the fact that the staff will need to travel to the site of the geothermal power plant during those operation and maintenance phase. And finally, in the end of life, the well will need to be closed, so some cement plugs will be inserted, which is considered with the energy needed for this abandonment phase and the mass of cement. So this is an overview of the reference model we developed, a reference model which has 26 parameters and from which it's possible to derive, for example, the amount of greenhouse gases. The amount of greenhouse gases emitted for Rittershofen will be made up of the amount of greenhouse gases emitted during the exploration phase, during the power plant construction and the well drilling, during the operation and maintenance, and also during the end of life. And as I mentioned, we want to have the amount of greenhouse gases emitted per kilowatt hour of heat produced over the plant lifetime, which can be derived using the equation shown on the screen. So once we have this reference parameterized model, we can then go towards the simplified model. The question now is, from these 26 parameters, which ones are the ones that explain most of the variability in the impact? We do that using the global sensitivity study and more specifically using Sobol indexes. We will be using first order indexes in this presentation, showing the contribution of each variable individually when all parameters are changed at the same time. And here you can see the parameters that are contributing the most to the variability of the climate change total impact category. We're using ILCD 2018 impact category. The heat output is a very important parameter, the well length as well, the power of the production pump, but also the number of production wells. Despite the fact that we thought that the direct emissions are quite low, they seem to be an important driver of the variability of the climate change, as well as the lifetime, the CO2 content in these direct emissions, and the operating hours. Altogether, those 8 parameters explain 87% of the variability. And here again, I'm stressing, they explain 87% of the variability of the impact category, not of the impact category in itself. From these 8 variables, we chose only 6. So we did not use the fraction of direct emission and the CO2 in the direct emissions to derive a simplified model for climate change. And these 6 parameters, they explain 83% of the climate change variability from the reference model. And again, to recap, the 6 parameters are the heat output, the well length, the power of the production pump, the number of production wells, the lifetime of the plant, and the operating hours. And the model looks something like that. The question now is, how does the estimation from this simplified model compare to the reference model? And you can see here on the screen that the simplified model on the x-axis is estimating values from how the simplified model is estimating values compared to the reference model on the y-axis. Ideally, we would want all the points to be on the dotted line, which is not the case, and we have an R-square of around 50%. And you can also see that most of the realizations of the model are between 0 and 10 grams of CO2 per kilowatt hour. Besides the performance, let's say, of the model, another important aspect is to know for which installation can the simplified model actually be used. It can be used for heat generating power plants. We saw that the volume for this simulation was not an influencing parameter in terms of variability. So we could say that our model is applicable for heat generating power plants as a whole. It's applicable for the French electricity mix, as well as I was mentioning, those heat generating power plants require electricity during operation, and I modeled the electricity using the French electricity mix, which will have an impact on the climate change total impact category results. Also for installations that have low direct emissions, so we use the boundary between 0.1 and 5%. And otherwise, the variables of the model should be within the following ranges. So the heat output between 10 and 40 megawatts, the well length between 1,300 and 5,500 meters, the power of the production pump between 200 and 1,200 kilowatts, the number of production wells between 1 and 2, and the plant has should have a lifetime between 20 and 40 years and operate between 5,000 and 8,500 hours a year. I will finish with a brief comparison with literature, or better saying that I was not able to compare with published results. The reasons were that there are few available SPA studies on the heat production from deep geothermal power plants, and there are even fewer studies that are within the simplified model boundaries. And some words of caution to finish, even if I would have been able to find this literature, it's not said that they would have been using the same impact categories and that the level of details would have been sufficient for me to apply my model on. But still, it's work in progress, and it's important to do this step to be able to have more confidence when we apply this simplified model. With that, I want to thank you for your attention, and there is a Q&A session, but in case we don't have time, please feel free to drop me an email.
Thank you very much, Melanie and Guillaume, for this presentation of the French case. Now we have the presentation of the Bagnore case in Italy, and it will be presented by Lorenzo Tosti, who is Research Fellow at the Center for Colloid and Surface, and Nicola Ferrara, who is PhD candidate at the University of Siena and Associate Student at the Center for Colloid and surface. So I think the first one will be Lorenzo.
Yes. Can you see my screen?
Yes, and we can also hear you well.
Good. So thank you, Valeria, for the introduction. I will give this short presentation just to introduce the Italian case study, Bagnore power plant. The Bagnore field is located in the Monte Amiata area, Tuscany, Italy. The field is characterized by two connected power plants, Bagnore 3 and Bagnore 4, which are realized and currently operated by the Enel Green Power. Bagnore 3 is a flash plant with 20 megawatt of installed electric power, and additionally 1 megawatt of electric power is provided by organic ranking cycle unit. Bagnore 4 is powered by two groups of 20 megawatt of electricity each. Additionally to the electricity generation, also the residual heat after the turbine expansion is recovered and provided to the final user. It is important to highlight the presence and the power plant is equipped with a mercury and hydrogen sulfide abatement system, which that significantly reduced the emission of mercury and hydrogen sulfide from the site. I'll give you some technical detail. Well, the geothermal source is hydrothermal type with a dissolved gas concentration between 6 and 9 in mass. On the top right side of the slide, you can see the composition of the non-condensable gases, which is mainly CO2, with a smaller amount of ammonia, methane, and hydrogen sulfide. The final energy use is primary electricity production. As I told you, the installed power is concerning the electric power is a total of 60 megawatt, whereas the thermal installed power is 21 megawatt. The heating is supplied at a temperature of 100 degrees with a returning temperature of 60. A total energy output on an annual base is 544 gigawatt for the electricity and 32 gigawatt for the thermal energy. According to the guidelines and the study that we presented here, the predicted lifetime is 30 years for the power plant. We have a total of 8 production wells and 6 injection wells for a total of almost 32,000 meters drilled and a pipeline length of a bit less than 10,500 meters. Well, this was everything concerning the general introduction. Now I will leave the floor to my colleague Nicola Ferrara for the parameterized model. Thank you all for your attention.
Hello, everyone. I hope you can hear me. And so I'm going to say something about the simplified model applied to this Bagnore case study. This is, as Lorenzo said, is an electric production flash power plant based in Italy. So this is a key
point for this simplified model. And the simplified model will explain the climate change impact category. So I will follow the same steps introduced by Isabel Blanc. And so the scope of the study, I mentioned that it's the determination of the climate change impact category of this power plant. And so the first step is the definition of the reference parameterized model. This is the main scheme that I applied for this power plant, and this was developed in a way that is possible in the future, near future, to apply this model to other power plants. So this is something that is general, more general than the binary power plant itself. And here I highlighted some important parameter. For example, for the well, I have the meters drilled, and this process will cover also the shallow and the deep well, because the binary power plant is characterized by both kind of well. And so also for the pipeline, the length of the pipelines and the equipment, which account for the commissioning phase, I use the number of wells and of course the installed capacity of the power plant. And also an important point of this model is the geothermal fluid composition. And this is also modeled considering abatement system, which in case of binary power plant is mainly the EMIS system, while the model is developed in a way that is possible to use also other kinds of abatement system. And also the needs of makeup wells is taken in consideration, even if for binary no power plant, no makeup wells were drilled. And so all of these key parameters are defined here, and so the minimum and maximum values try to cover wider fields than the binary case studies, but the default one is the values I used to model to test my simplified model for binary case study. So this model now have 15 parameters, but all of these work are in progress. So this from starting from now, everything is something preliminary results. So all of this will be expanded and will be something that will change. So, for example, the average load is something that it's taken into consideration. So these are all the parameters that are taken into consideration. There are something that is defined by the guidelines. So the lifetime, for example, that is default is 30 years, but the parameter spreads from 20 to 14 years. And also the installed capacity for binary is designed to be 61 megawatt, but the model it's modeled to have to spread from 20 to 120 megawatt hours. And also the composition of the non-condensable gas, and this model is designed to be applied in a field that has content of non-condensable gas from 0.6 to 12% of non-condensable gas, with main content of CO2 and methane, CH4. And so the operating hours is something that it's also taken into consideration, and spreading from 7,000 to maximum ability of the power plants. And there is also a parameter that is specific for the binary power plant, which is the EMIS vulnerability, which is the amount of hours in which the EMIS abatement system is not available and so this abatement system is not working. So the model developed in this way it's expressed for the climate change impact category using both all the 15 variables. It's look like this. So it's a quite complex function that needs a lot of variables to assess the climate change impact categories using the ILCD 2018 method. So by means of the Sobol indices, I selected the method allowed to select just 3 parameters, which explain quite large variance of the model. So 91% of the variance is expressed by these 3 parameters. Parameters that are taken into consideration is the flow rate, so the geothermal flow rate of the fluid that is going into the turbine expressed in kilograms hour, the mass fraction of the non-condensable gas of the geothermal fluid, of course, and the installed capacity of the power plant, which is expressed here in kilowatt hour. And so the application of this function will generate this dispersion. So by means of Monte Carlo simulation, 22,000 of points are calculated, and this is the distribution of the simplified model versus the reference model. So the median line is the reference model, and as is possible to see, the simplified model it's going to a little bit overestimate the reference model results. But still, the R square is quite high, so the function is quite well fitting the reference model results, so 0.9 R square. And so the key condition to have this function applied in other system is this. So the flash geothermal system needs to produce only electricity, because at the moment this model will account only for electricity production with a medium to high content of non-condensable gas, so 0.6 to 9% in mass of the non-condensable gas content, and these gases needs to be composed mainly by carbon dioxide. And also the flow rate is between 100 and 800 tons hour, with an installed capacity ranging from 20 to 120 megawatt electric. And so, as I said, this function will give the results complement to the ILCD 2018 method. And this model, I test this model with literature, and the comparison gives good results. In fact, as you can see, the simplified model is very well based in respect to literature works that are these literature work I considered are taking accounts Italian power plants. So something that needs to be clear is that this kind of model is very site specific, because it takes in account at least the key variables. One key parameter selected is the content of non-condensable gas, so these parameters is very site specific. So this is something that is very important for this simplified model. But in any case, the results given by my simplified models is good, and even if the statistical descriptors shows a little overestimation of the results from the simplified model. So further development for this model is the correlation between the geothermal flow rate and the installed capacity. So in this way, it's possible to reduce the input parameters dimension needed for the simplified model, and also in this way, it's possible to avoid the overestimation of the results. And also, the one important task is the development of the simplified model also for heat generation and both heat and electricity generation power plant, because it's something very important for this kind of energy source. So thank you for your attention.
Many thanks, Nicola and Lorenzo. Now Virginie Arquette-Menou will present the Belgian case, Balmat. Virginie is a senior researcher at VITA, the Flemish Institute for Technological Research, specialized in clean tech and sustainable development. Then also Nicola Ferrara will present one part as well, and Lisa Damen from VITA as well contributed to the presentation. Virginie, the floor is yours.
Okay, thank you very much. Hello, everyone. So as said, I will introduce the Belgium case study, for which the simplified model is actually being developed still at the moment. So it's still work in progress, but still we wanted to give you first an overview of the geothermal system that we have in Balmat, and to give a first definition of the LCA reference model. So the Balmat geothermal project is located at the headquarters of VITO, the Flemish Institute of Technology. The project started in 2009 with a feasibility study. It is important to say that it is a demonstration project. So the aim of the project was to somehow pave the way for realization of further geothermal plants in the Kempin region. The geothermal wells supply heat to an existing district heating network, heating the campus of VITO and neighboring companies. So here SCK-CEN and Belgo Process. The heat demand is about 25,000 megawatt-hour per year, and the temperature regime is between 95 and 70 degrees Celsius. It is important to say that additionally to the heat delivery, the unused heat from the wells, so mainly in summer, when the heat demand is low, can be used to produce electricity by means of an ORC installation. Also interesting to say, the district heating network is currently operating at high return temperatures of about 75 degrees in winter condition and 65 degrees in summer condition, resulting in quite high reinjection temperature of about 80–70 degrees Celsius. The geothermal capacity that is installed is split between electrical installed capacity with a demonstration ORC of 0.25 megawatt electric, and a thermal capacity installed of 6.6 megawatt thermal. When it comes to the reservoir characteristics, the reservoir depth is between 3,200 meters and 3,600 meters, so it's a deep reservoir. It consists of fractured carboniferous limestone, and the bottom hole temperature that has been measured is about 139 degrees Celsius. At the moment, we have 2 operational wells, plus 1 well that was foreseen for production. The first well, MOL GT01, is a production well. It is a vertical well, and the depth that it reached is about 3.6 kilometers. It was achieved in January 2016. Because testing of the well was successful, we went on with drilling of a second well, an injection well, MOL GT02. This well is a deviated well. It reached depth of 3.8 kilometers, but the actual drilled length of the well is more than 4 kilometers, and this well was achieved in September 2016. The two wells received chemical treatment. MOL-GTO1 was stimulated twice with chemical stimulation, whereas MOL-GTO2 was stimulated once with chemical stimulation. In addition to these two operating wells, we have an extra well, as said, foreseen for production, MOL-GTO3, that is highly deviated. It is very deep. It's more than 4 kilometers deep. And the actual length that was drilled is 4.9 kilometers. This well was achieved in July 2018. Unfortunately, at the moment, we cannot produce from that well. The brine at Balmat is of sodium calcium chloride type. The salinity is very high, 165 grams per liter. And we have also a quite high gas-liquid ratio. For every cubic meter of brine that is produced, 2.3 normal cubic meter of gas are co-produced. The gas consists mainly of CO2, more than 75 volume percent, and we also have methane. The plant description is as followed. It's the building of the plant started in 2017, and we are still in a testing phase since November 18. The production temperature at the moment that was registered was between 121 and 126 degrees Celsius, and the average production flow rate varied between 70 and 150 cubic meter per hour. At Balmat, we have one primary loop where the brine circulates and one transport loop with fresh water. Because we want to avoid as much as possible NCG emissions, the geothermal loop is pressurized and the injection within the surface installation is about 40 bar. We have one downhole electro-submersible pump and two heat exchanger with a total capacity of 6.6 megawatts. As said, at the moment, unfortunately, the plant is not in operation due to some induced seismicity issue that we are solving. And we can only give at the moment for this LCA study numbers concerning the plant once it is in full operation. At that stage, once in full operation, the plant will be used to supply about 50 gigawatt hour per year, 50% for heat delivery, 50% for electricity production with 10% efficiency. And the amount of electricity that will be consumed will be about 3,300 megawatt hour. And I think by now I can give the floor to Nicola, who will give information about the LCA reference model that is being built for the Balmat case study.
Okay, thank you, Virginie. So this model is still in development in order to address all the characteristics parameters of the Balmat power plant. For example, the possibility to share the production between heat and electricity. So this is the reason why this task is ongoing. But this reference model is valid mostly for the geothermal power plants. So we have a commissioning phase with the well drilling, the geothermal loop building, the equipment, commissioning, and so the electric submersible pumps, which is an important part for this power plant. So then going through the operation and maintenance phase, It is characterized by the possibility to share the production between heat and electricity. So the electricity, for example, can be used for self-consumption or put it into the network. So this is a quite complex task to address in a simplified model. And also the power of the pumps is key parameters that need to be explained. And then to go into the decommissioning phase, there are two main processes that are described. So the plant decommissioning and the abandonment of the wells. So this is a quite general reference model. And so, but at the moment, this is what is something that needs to be developed a lot. So this is it, and thank you again for your attention.
Many thanks for this presentation. And now we can go to the question and answer session. I see there is already here one question for Lorenzo Tosti from Sanjay Kumar. How many tons of CO2 emissions are released from 1 megawatt? I think the speakers can just unmute themselves and answer.
Can you hear me?
Yes.
It's about, if I'm not wrong, 0.8 per kilowatt. 0.8 kilograms of CO2 equivalent per kilowatt. I don't have now numbers with me, but that's the order of magnitude. There's also a graph in Nicola's presentation with these results.
Thank you, Lorenzo. There is another question. If you want to have a discussion, you can also raise your hand, and we can unmute you, and you can ask the speakers directly. So there is another question from Gianpaolo Manfrida, who is asking that the SLCA were shown only for CO2, and for this category, the SLCA and LCA are in good agreement. He expects that for other relevant categories, like human health, damage to the environment, health effect, the agreement is much lower, and most of the incentive bounds is much larger. So this is a comment from Gianpaolo Manfrida. I don't know if somebody wants to comment on this.
I didn't quite got the question, so I understood that Gianpaolo Manfrida is asking about different modeling for other indicators, and so if I understood well, I can answer that it may well that the key parameters for human toxicity, for example, will not be the same as for the climate change indicator. But I don't know if I'm answering to the right question.
There is another question from Sean Porce, the US Department of Energy, And he's asking if somebody can comment on comparable LCA values for other renewable energies like solar or wind or other renewable in general.
Yes, it's Isabelle Blanc speaking. Yes, we did assessment for other renewable systems. And for example, for photovoltaics, I would say that it is a range going from 10 grams of CO2 equivalent till 70, 80 grams of CO2 equivalent. It seems to be highly variable, but it is normal because it depends on the technology of the panel. It depends where the location is implemented, the photovoltaics. And for example, in France, from north to south, you could double solar irradiation from north to south. So because the carbon footprint is expressed per kilowatt hour, then for the same panel, depending on the amount of electricity you can produce, you have single to double performance. So this is for photovoltaics. We also did some assessment for wind turbines, onshore or offshore. Offshore turbines might even go below 10 grams of CO2 equivalent, but this is very for specific condition with high wind speed. I would say that these are figures you could find for photovoltaics or wind turbines.
Thank you, Isabelle. There is a question for the Balmat project about the seismicity size and if it was too serious to stop the project.
Hello, so it's Virginie speaking. I think I can answer this question. So the magnitude of the events that we had last year was about 2.1. So we had no real damage or anything, but it is important to be able to proceed with the project to really understand what caused this event. And at the moment, we are still working together with some other research institute to really look into the data that have been recorded. And we are now working also on putting on additional seismometer on site to better monitor the seismicity. So it was not enough to have really damage, but still it was enough to stop really the project, so that we had more data and to have better insight into the phenomenon that happened.
There is a follow-up question, actually, Virginie, on this, if it is proved that this was related to geothermal operation.
Well, I am not actually the one really following on that in my team at Vito, but what was seen is that it was quite close to the injection well, but I can't say much more on that because, as said, I am not the one following this topic, and they are still looking into the data. So there are good chances that it is due to the injection, but yeah, we are still processing the data.
Okay, thank you very much. One last quick question, if somebody can recommend scientific studies that incorporate both heat and power generation? Does somebody want to pick up on this question? Otherwise, we can always come back by email. Okay, I think we've reached the end of the webinar. Well, we hope that all of you enjoyed and found it interesting for your work and relevant for your work. If you're interested in the final result of the LCA tool and of GEOENVI project, you can see here you can go on our website, geoenvi.eu. You can also follow #GeoEnvi on social media. We have Twitter, Facebook, LinkedIn. Soon we'll have a video about the GeoEnvi project, and you can write to us to communication@geoenvi.eu. I thank you very much our speakers for the time and for the explanation they give us today, and to all of you for following us until now before lunchtime. So have a very nice day, and I hope we all keep in touch. Bye. Thank you.